Thanks, everyone. I'm very happy to be here. And yeah, today I will be talking about this approach for flexible and scalable tuning of hyperparameters using hypergradients. Okay. These slides, by the way, they are based on some lecture notes by Roger Gross. Roger, he's a very good friend of mine, and we can also have a look at the work that he has done. He has done a ton of interesting things. Good. What I'm going to present here is a general introduction to optimization with hypergradients, but I will focus in particular to this work that was done in collaboration with two PhD students at Cambridge, Ross Clark and all the ways. Good. So let's start. We're interested in tuning hyperparameters. Hyperparameters appear in almost any machine learning method. Neural networks, they have tons of hyperparameters, learning rates, regularization parameters, weight decay, momentum, and many others. And tuning these hyperparameters is usually expensive. Typically, you have to choose some value of these hyperparameters or knobs. And then you run your machine learning method, you see how well it performs on some validation data, and based on that feedback, then you find new settings for the hyperparameters that you expect to work better and repeat the whole process. And then there is this kind of inner optimization that tunes your weights given your hyperparameters, and then another outer optimization that tunes the hyperparameters. This is in practice very expensive, and ideally you would like to accelerate these things. How you could do this? One way to do it is to actually use gradient-based optimization. Gradients can give you a lot of information about how to tune your hyperparameters. Ideally, we would like to do that. So by using gradients, we will be able to do things much faster than if you follow black box methods for hyperparameter tuning. A very popular thing is to use maybe base-up, for example, or other techniques to tune hyperparameters. And many times you have to train your method many times and use this feedback to improve the selection of your hyperparameters. And that can be quite slow. Ideally, you would like to train your method, and you are adjusting the weights, but at the same time that you adjust the weights, you can also adjust the hyperparameters using gradient-based information from your validation set. And ideally, that's what we are going to aim to do here. Good. So let's have a look at this hyperparameter optimization problem in detail in a more formal way. And I include here a definition of the things that we're going to be working on during this lecture. We have first the training loss, which we are going to denote with this calligraphic LT. This is the training loss that we usually minimize to tune our weights in a neural network. I'm going to be focusing here, by the way, mainly on neural network models. We're going to be optimizing the weights of our network on the training set, optimizing this training loss. But then we have this validation loss that we use to see how well our network will be generalizing. Once we have chosen a particular setting of the weights, we have optimized these weights and given the hyperparameters and maybe given some optimizer with its own hyperparameters, then we look at how well the method does on some validation loss. And that's what we are going to try to maximize to improve. We will be minimizing the validation loss. We want to improve on this, okay? As I said, we are tuning the weights, the neural network weights, which we represent with W on the training set. We are going to denote the hyperparameters with this letter lambda. And then once we have optimized the weights on the training set by minimizing the training loss, we assume that we have some optimized weights, which we are going to denote with W star. And then what we want is to optimize the validation performance, the validation set performance with respect to the hyperparameters, and the optimal hyperparameters, we're going to denote them also lambda star. So the whole optimization problem has these two level optimization process. This is often called a bi-level optimization process. First, on the training set, you tune your weights, and that is going to give you some optimal weights, W star, and obviously these optimal weights are going to depend on the hyperparameter, lambda. Maybe I have these regularization parameters, maybe weight decay, and they're going to affect the optimal W star that I obtained. But maybe I have learning rates and momentum, and that's going to depend, that's going to affect also the value of the W star that I obtained. Okay, and then we're going to take those optimal weights, we're going to put them into our validation loss, and we're going to evaluate that. And our goal is to optimize that validation loss with respect to the hyperparameters lambda to find the optimal hyperparameters lambda star. Once we solve these problems, we have lambda star, W star, and then we could make predictions with the corresponding W star for lambda star. Okay. As I said, this is called a bi-level optimization problem, and it's kind of complicated because the hyperparameters in the validation loss they determine the value of when we evaluate the validation loss is going to depend on the hyperparameters through W star. Okay, and that's going to create some difficulties when we try to solve this problem. Okay, this W star is called this best response function. Okay, and it just represents the optimal weights for a particular setting of the hyperparameters. By the way, if anyone has any question at any point, feel free to ask. Yes.
What happens if this optimal solution regarding the training process is not unique and can wobble around? I mean, you can observe such effects if you use one regularization, for example, and the performance landscape, if you would plot it against, so performance against one regularization term, would have a concave part, so it's not a complex function, basically. And then you can end up either on the one side or the other side of this concave part, but not in the middle if you use weight sum approach. So how to do that?
Yeah, we're going to simplify things here, and we're going to assume that you just find some local optima. We're going to see later what is going to happen in practice is that here you don't really fully optimize your training loss. And we're going to see methods that will be able to deal with that. But at the beginning, right now, we're going to assume that everything is kind of simple, and let's assume that there is like a unique minimizer for a particular setting of the hyperparameters on the training loss. And we're going to see later on things that we could do when this is not the case. I mean, in practice, it will never be the case that you will just converge to a single optimal solution, because you will just be running your optimizer for a few steps, and maybe you don't even really converge to anything. So, so we'll see what happens in that setting. Okay, cool. Any other question at this stage? No. Good. So this figure kind of illustrates what's going on here. We have some space of hyperparameters along this axis. This would be like the axis of lambda, and then this would be the axis of W. And we're interested in optimizing this training loss, which would be the vertical axis here. And then we see that for different values of lambda, you will have different optimal solutions for W. And this is represented by this curve in black that represents the minimizers of the training loss for a particular setting of lambda. As a function of lambda, the black line represents the minimum point that you obtain for W. And then this is actually the best response function. This curve in black, it represents the optimal weights for a particular setting of the hyperparameters lambda. And we can represent this as this function in blue. Okay, and then what we're interested is in translating this function, combining it with the validation loss, which is what appears here on the left. On the left, here you have on the vertical axis is this validation loss, and you see that it just seems to be, this is like a toy problem, so it seems to be just decreasing as you reduce the value of the parameters W. So you will be just taking your best response function, the blue curve, and then you just look at the values that you obtain in the validation loss as you move through this best response function. And the result is the validation loss as a function of the optimal weights which is represented by this curve in red. Okay, the curve in red represents the validation loss that you obtain for the optimized weights as a function of lambda. Okay, you choose a value of lambda, you optimize the weights to obtain W star on the training set, and then you look at the performance of those optimal weights on validation data, and you obtain this curve in red. And that's what we care about minimizing with respect to lambda. And we're going to be interested in optimizing that using gradients, okay? And the gradients could be represented by this dotted line here. This could be the gradients that you obtain for a particular value of lambda, maybe this one. Yes.
Is there a specific algorithmic scenario you were like focusing on? Because I mean, the title says optimizing millions of hyperparameters.
Yeah, this is a reference. I'm not going to focus on this paper at all. But yeah, this figure is extracted from this paper, and I think in this paper they use they optimize the training data, for example. So you could say I want just a small subset of data points, and I will be even optimizing this data. You could consider kind of your data as hyperparameters.
So you get like a weight for you, or you're really optimizing the data points themselves.
Yeah, what you could even do that, and that's what they do in that paper. I'm not going to go into that in this talk, but just to give you an idea, because you're using gradients now, you can optimize, I don't know, as many hyperparameters as you want. I'm going to include results where you tune learning rates, and you have one learning rate per dimension.
Yeah.
So this means that you have like tons of hyperparameters. Okay. Good. So what we're interested in is in this gradient of the validation loss with respect to the hyperparameters once you have evaluated the validation loss on your optimized weights. And this gradient is going to be called the hypergradient, and we're going to be calculating these things. Good. Any questions at this stage? No? Good. So we're going to use gradients, and we need to be familiar with some basic concepts of gradients. We're going to be using heavily something called the multivariate chain rule. And it's as simple as this. If you have a function f that depends with respect to some inputs through other functions, for example, g1 up to gk, and you want to calculate the gradient of f evaluated on all these, the output of all these other functions, and then you're going to calculate the total gradient with respect to x, you can show that this is a sum of the product of the gradient of f with respect to the individual functions times the gradients of the functions. Okay, this is called the multivariate chain rule, and you can obtain it very easily by just saying what is the gradient of f, and we're going to call y the output of all these functions g. We just represent that as a vector. So we just have f of y. This is the function that we are interested in, and we want to calculate the gradient of this with respect to x, and you can just say the differential of f divided by the differential of x. That's the same as differential of f divided by differential of y times differential of y differential of x. Okay, simple gradients. We're going to be using this heavily to calculate these hypergradients. Okay, I assume everyone is familiar with this. Yes, some question?
Yeah.
No. Good. So what is the hypergradient? We're interested in the total gradient of the validation loss when we evaluate it on the optimal weights W star that we obtained by tuning them on the training set. And the optimal weights are going to depend on lambda, obviously, and there is a possibility that the validation loss also depends on lambda. Okay, so we are interested in this total gradient, and now the validation loss is obtained as a function of lambda in two ways, as we show in this computational graph. So through lambda, you optimize the weights on the training set, and you get W star, and W star obviously depends on lambda, but there could be that the lambda also affects the validation loss in some way. So you have to account for this when you calculate gradients, and that's why you obtain this formula for the total gradient of the validation loss with respect to lambda. That's going to be the direct contribution of lambda on the validation loss. You will have to take the gradient of that. Okay, this could be corresponding to this arrow here. you will be calculating the partial derivative of the validation loss with respect to lambda. And then you have the dependence on lambda through the optimal weights. And that's why you add this extra term here. It's just the derivative of the validation loss with respect to the optimal weights. And then you need to multiply by the gradient of the optimal weights with respect to lambda, okay? And we have these different terms. That's all we need to calculate these hypergradients. It seems like a simple expression here to obtain the gradients, but as we're going to see, it's going to be tricky to calculate these gradients. In particular, these gradients with respect to the optimized weights with respect to lambda, okay? Because that means that actually, if you wanted to do this, you will have to differentiate through your whole training procedure, and that can be quite expensive. In many cases, you won't be able to do that, and we're going to be seeing different ways to approximate these gradients, okay? So yeah, as I said, this is called the hypergradient. It tells you how you have to change your hyperparameters so that you improve your validation loss, okay? And you call it hypergradient because the gradient usually you use it for example, when you tune the weights and so on. Great. So how do you calculate this? There are different terms in this expression. The first one is the gradient of the validation loss with respect to the hyperparameters, the directed contribution of the hyperparameters to the validation loss. Okay. Typically, this term is very simple, and in most cases, actually, the validation loss is not going to depend on hyperparameters. Imagine that you want to tune optimizer hyperparameters like learning rates, momentum, and so on. The optimal weights will depend on them. But then once you have the optimal weights, W star, the validation loss doesn't depend in any way on those parameters. The same happens with weight decay. You may have weight decay. The weight decay regularization doesn't appear in your validation loss. So most of the times, this gradient is 0, and it means that you can ignore it, and that's great. But in other cases, maybe you have to account for this. There are some cases, for example, if you are tuning an architecture of a neural network, and maybe you want to penalize maybe, I don't know, memory and maybe arithmetic operations or so things, it could be that this gradient is not going to be 0, and you will have to account for that. In almost all the experiments that I'm going to show here, this gradient is going to be 0. But if you are thinking of a particular application, you will have to take it into account. Yes?
So very often the lambda will be in discrete space.
We're going to assume, yeah, so what happens if lambda are discrete? So we're going to assume continuous values for these hyperparameters. The question is, what happens if some of your hyperparameters are discrete? For example, if you're optimizing your neural network architecture. Some people, what they do is they assume a smooth relaxation of these discrete parameters. So they will assume that the parameters are continuous. They will optimize them, assuming that they're continuous, and then they will have some discretization step at the end.
Yeah, does that make sense?
In some cases, maybe yes. In others, maybe not. It depends on the problem. Some people have been quite successful doing those things, but it's a limitation of these techniques based on gradients. Obviously, that you may have discrete parameters, and you might not be able to tune them exactly. What I'm going to focus here is on continuous parameters. Good. So let's have a look at the other terms. We're going to call them the best response term, because it depends on, I mean, there is this best response function here affecting this. And now this represents the gradient of your validation loss that comes indirectly through the optimal weights. It represents this path in the computational graph. And then here, as we're going to see, it's going to be a bit more tricky how to calculate this. We have two terms here, the one in blue, which is just the gradient of the validation loss with respect to the optimal weights. This is actually very easy to obtain. It's just like you do it, it's the same as what you would do for training your neural network. You just do like a back probe on a mini batch on your validation data, and you will get an estimate of this. Okay, so this term, the gradient of the validation loss with respect to the optimal weights, that's very easy to obtain. Usually, we shouldn't worry much about that. And now we have this other thing called the best response derivative. Okay, and this is the gradient of the optimized weights with respect to the hyperparameters. And that's where the tricky thing happens here. it's going to be harder to obtain this. In practice, you won't have a closed form expression for this, and you will have to do approximations. And we're going to see different ways in which you can deal with this. Okay. Good. Any questions so far on this? No? Good. So let's have a look at actually what is this derivative of.
There might be 1 or 2 questions over there.
Okay.
You guys are my questions about the last activity, the
Okay.
last presentation.
The last presentation, the last slide, you mean? The previous one?
Yeah, this one. And in fact, in most cases, this equation equals, but there are some many local minimal optimal solutions in this equation. There may be some many local minimal solution. Yeah.
Yeah, so this is not that yeah, so when this gradient is 0, it doesn't mean that you get like an optima for this.
Yeah.
It means that the validation loss does not depend on the optimal hyperparameters directly. So you could think that this arrow here doesn't exist.
I mean, if you find the local minimal solution, are there any measurements? Are there any? If you find the local optimal solution,
Yeah. So this is not really related so far to local optima. We're going to see maybe later what happens with local optima and all that. But here it's not like they are local optima or anything. Sometimes this arrow here doesn't exist because when you calculate the validation loss, you don't use lambda directly. You only use W star, and then that's why you can ignore this part. Okay. Any other questions? Yes.
You said that in most cases the derivative with respect to lambda is 0.
Yeah.
So would you have to check that, or can you just assume?
I mean, you know it when you specify your validation loss. Your validation loss will depend on W star, and maybe it depends on lambda or not. And I mean directly on lambda. So when you write your validation loss, you will write like some expression, and it's going to have W star there, and maybe there is some lambda there. If there is a lambda there, then there is a gradient. If there is no lambda, then there is no gradient.
So you're coming to this conclusion formally.
Yes, you know that beforehand. So as soon as you
this-
specify the validation loss, you know if this happens or not.
Okay, yeah, so it's not exploring. Okay,
Yeah.
so
Good. So let's try to calculate this tricky term. Let's try to see, okay, this is going to be more complicated. The derivative of the optimal weights with respect to the hyperparameters. What is this derivative? It turns out that under some conditions, we can actually obtain this derivative. Okay, we're going to assume that you fully optimize your weights W star on the training set, and this means that for a particular setting of lambda, you obtain W star, and you fully optimize your training loss, and this means that the gradient on the training loss with respect to W star is going to be 0. Because you have converged to a local optima. And this is going to be 0, this gradient is going to be 0 for all the values of lambda. Okay, you choose a value of lambda, you get your optimal W star, and that's locally optimal for that value of lambda. So the gradient with respect to W star of the training loss, then it's going to be 0 all the time. And it doesn't matter if you change lambda, it's going to be 0 as well. So if you derive this with respect to lambda, you will get 0. Okay, and then you can see what happens in that case. You can write now this gradient, the gradient of the training loss evaluated at W star, and then you calculate the gradient with respect to lambda on this, and that's going to be now as before. You're going to have now a direct contribution with respect to lambda, and then an indirect contribution with respect to lambda with respect to W star. Because W star depends on lambda. So you just calculate this gradient. It's the same as before, but we have replaced the validation loss with the training loss, and not really the training loss, it's the gradient of the training loss. So it's more or less the same as before, and you know that this is 0. And this can be used to find the value of this gradient of W star with respect to lambda. You can just solve here for W star, the gradient of W star with respect to lambda. That's going to be minus the term on the left divided by this second derivative. And this is what you obtained here. This is an expression now for the derivative of W star with respect to lambda. And you have here now the inverse Hessian of your training loss minus the inverse Hessian of the training loss times now the derivative of the training loss with respect to W star and then with respect to lambda. So now we have actually an exact solution for this derivative. And we could in principle use this to tune our hyperparameters. But we run into problems if we do this, okay? We're going to run into problems. First, we have an inverse Hessian here. This doesn't look very good. There's some questions.
It also assumes that I'm not doing stuff like early stopping, right?
Yeah, that's right. We're going to see later what would happen in those cases, but yeah, we assume that you train fully.
Yeah. So
you could imagine that if you don't convert, maybe this is still a reasonable approximation.
Yeah, this is fine.
So maybe you didn't really fully convert and you could use this. But you have an inverse Hessian, and that's problematic because Hessians in neural networks is a matrix which has size number of parameters times number of parameters, and this is a massive matrix. You don't really want to work with that. And here you have even the inverse of that matrix, which is horrible. So you are starting to run into problems here. So the other thing is, okay, that's very good, but what happens with the optimizer hyperparameters? Maybe you have learning rates. What is the gradient now with respect to the learning rates? Imagine you have a learning rate. Then here you have the Hessian of your training loss. That's fine. That doesn't. It's going to be some positive thing. And then you have here the derivative of the training loss. First, you will calculate the derivative of the training loss with respect to W star. This is like a backprop that you would normally do. And then you need to see how that changes when you change your learning rate. And then you say, it doesn't change, no? It doesn't matter what my learning rate is. My backprop is going to be always the same. It doesn't really depend at all on a learning rate. No, I have W star, I have convert my optimizer, or I stop my optimizer, and then I do a backprop, and then I would have to do a derivative with respect to the learning rate, and this would be 0. So you don't really get a gradient with respect to learning rates, for example, okay? And this is kind of not satisfactory. So this doesn't really tell you exactly how to tune learning rates, and you have these problems with the Hessian, so you will need to do something to deal with this. We're going to see later actually how to actually properly deal with learning rates. And we're going to obtain a similar version of this implicit function theorem that actually can account for learning rates. We're going to see that later. Good. Any questions so far on this? No? Good. So let's try to still somehow approximate this. Okay. So this was the hypergradient. We have now used the expression that we had before. This is 0, so we can forget about it. And then we have the validation loss, the gradient of the validation loss. That's easy. We have the inverse Hessian here that is annoying, and then we have these gradients that maybe they're easier to work with. So then what we can do, what can we do here? One thing that you could do is to try to approximate this inverse Hessian product. Okay, we have an inverse Hessian times another matrix. Let's try to approximate that. And there are different ways that you could approximate that. You could think about approximations of the inverse Hessian and use those. There is another thing that you could do. You could say you just optimize W through many steps, and then you backprop through all those steps to get how W star would change as a function of lambda. Okay, you could be training for many steps to obtain W star, and then you backprop through all that process to obtain the derivative of W star with respect to lambda. And this is often called unrolling the inner optimization and differentiating through it. And that's something that we could consider. It has some limitations as well, as we're going to see, but it may work in some settings. And then another thing that is what I'm going to focus more in this lecture, which is a hybrid approach that is going to combine ideas from both. Okay. So now let's get going and let's see how these different methods work. Any questions at this stage? No? Good. So we're going to work with a Hessian, and we want this inverse Hessian. So how can we actually work with a Hessian, which is this massive matrix in a neural network? How can we do it in an efficient way? So it turns out that you can do Hessian vector products efficiently. Even if these matrices are huge, you can multiply a vector by that matrix and get another vector in a cheap way. And you can do it easily as follows. Imagine that you have your Hessian, which would be this massive matrix, and you want to multiply it by a vector. That's the same as multiplying the second derivative of the training loss with respect to the weights times a vector. And now you can actually get the vector into these differentiation operations. So you can actually multiply the first derivative of your training loss with respect to the vector. And then you will get a scalar, and then you could differentiate that. And then that's actually like similar to two backward passes, and that's going to be efficient. Okay, so you can actually do efficient Hessian vector products, and maybe you can exploit this in the calculations. We're not really solving the problem because we needed the inverse of the Hessian, which is way worse than this. But maybe we can approximate the inverse using these Hessian vector products. Okay, so that's something that we could think about. So this is one way to calculate Hessian vector products. There is another way which is a bit faster, but it's more numerically unstable. I included here for reference, but you have to be careful with this because it will be faster, and in some cases it might be fine, but it could lead you to numerical problems, and maybe your speedups are not worth in practice. So let's assume that you have the gradient, this function g, and then obviously the Hessian is the gradient of the gradient. Okay, we're going to denote the Hessian with h of x, and you're evaluating your function, the gradient, and the Hessian at some input x. You can do a first order approximation of the gradient, and that's going to be the gradient plus the Hessian times some small increment. Okay, and the same happens if you just do the increment in some direction v. So r here would be something that is close to 0, and you just have that the gradient evaluated at some input x plus a small change in a direction v. You have here a first order approximation. And then you can just use this. Obviously, you could do it with minus RV. And then this is going to be the gradient minus RHXV. And you can actually then add the first one and subtract the second one. And what is going to happen is that the gradient goes away. And here you just have twice R times the Hessian times V. And if you just want the Hessian times V, you just divide by twice R. Okay, and this is what you have here. This is now an approximation of a Hessian vector product. Okay, and to do this, you just need again 2 backward passes, but these are just like normal backward passes. It's not like backward over the gradient times a vector. This would be slightly faster than the previous method. You will have to choose a small value of R. There are some rules to do this, where this could be like your numerical precision. I won't go into the details of this. It's just how to choose this value of R so that you try to minimize the numerical problems. As I said, it's faster than the previous method, but it can be numerically unstable. So actually, most people don't really use this in practice. There are some methods that actually use it, and it might be fine, but you have to be careful with the numerical stability problems. Any questions on this? No? Okay, so these are just, yes.
Is it common in this method to have whole smooth for the loss?
To have
to whole smooth, because if it's not smooth enough, there will be interval, right?
Yeah, it could be related to the smoothness of the loss. I don't really fully understand when this is stable or not, because it depends on the on the calculations that you do. But it could be that, yeah, maybe the smoothness is related to that. Yeah, the numerical problems will depend on the magnitude of the values. Maybe the gradient is very large. Yeah, it could be that if the gradient changes very fast as a function of r, maybe you run into more numerical problems. So yeah, there could be factors there. I don't really fully understand it, but yeah, the smoothness of the loss could be a factor there as well. Cool. So how can you use these Hessian vector products to approximate now products with respect to the inverse Hessian? There is something that you can do. One approximation that you can do is called this Newman series approximation of the inverse Hessian. Okay, and this is very simple. It's just what you normally do with power series. So if you have a power series with some term, imagine that you have maybe alpha, which is between 0 and 1, and you just add alpha to the 0 power, alpha to the first, to the second, and so on. That's a power series, and you know that that converges to 1 over 1 minus alpha. Okay, you can use exactly the same thing with matrices, and you can obtain an approximation to the inverse Hessian. Okay, so you want the approximation to the inverse Hessian. You can do now a power series that is related to the inverse Hessian. We don't want 1 over 1 minus lambda minus alpha. We want just the inverse of alpha. So you can just work with 1 minus alpha. You can do powers of 1 minus alpha, and you will get the inverse of alpha there. And that's what you do here. You're going to do now powers of the identity minus the Hessian. And you're going to raise that to powers. You're going to have a power series here now. And you know that this is going to converge to the inverse Hessian, provided the eigenvalues of the Hessian have magnitude less than 1, because otherwise the whole thing will diverge. It's the same thing as this scalar alpha that I mentioned before. If the scalar alpha is larger than 1, the whole series diverges. Okay, so what you can do to avoid this, you could have a constant here, a, multiplying your Hessian, and this constant, it could be a small number. And this will guarantee that you converge to the inverse Hessian. Okay, you just have to remove this scaling by multiplying by a later on. Okay, this is called I think you would say Neumann in German, like Neumann series approximation, and it involves multiplying with the Hessian, because it's only powers of the Hessian. So now you can do Hessian vector products. You may have to do a lot of those products, but you will obtain an approximation to the inverse Hessian. So if you have an inverse Hessian times some matrix, then you can just take a series like this, you truncate the series at some point, and then you just multiply the value of your truncated series with the matrix. And now you obtain an approximation of the inverse Hessian times a matrix. Okay? Good. Any questions on this trick with the power series? Is that clear? Well, just to clarify, all this is based on the fact that if you have a series like this, this is 1 over 1 minus alpha. Okay, alpha is between 0 and 1. Okay, and you don't want the 1 over 1 minus alpha. You want the inverse of alpha, and that's why you do the power series with 1 minus alpha. Okay, and you work with the identity minus the Hessian. Good. One question?
Yeah, just one question. Like, what happens when the Hessian is in positive definite to begin with and is inverted?
What happens when it's not positive definite? Yeah, typically that would be like some weight decay thing. Here, because it's a power series, you might be fine.
Okay. Yeah.
So you will just truncate your series, and we're going to see later that there is a connection between this power series and differentiating through the optimization, and that's going to be quite insightful to see why this approach may make sense. You may think, oh, this power series is just truncated, and it's actually just maybe a very poor approximation. You can show that this power series is equivalent to, or very similar. It's going to be very similar to just differentiating through your optimizer in a way that is going to save memory, as we're going to see later. So that's going to be having some interesting advantages using this Neumann series. Good. There are still some problems here. You can do the inverse Hessian product or approximate it, but you're still running into problems with tuning the optimizer hyperparameters, like learning rates. You're still running into these problems. And then obviously you may have to repeatedly find W star. So every time you want to calculate the hypergradient, you need the W star, and maybe that involves like running a whole series of optimization steps. And this could take very long. So you may want to deal with that. We're going to see how you can do that later as well. Maybe you don't really fully optimize to get W star. You only do a few steps of optimization. Good. The Neumann series is one approach, but there is another thing that you can use, and this is also like a very general useful tool. It's called conjugate gradients. Conjugate gradients can be very useful. It basically solves things like this: A times X equal to B. So if you have a big matrix A, and you want to find some product of the inverse of that matrix times a constant, you want to solve this system over X, and you can do it with something called conjugate gradients. And it's pretty similar to gradient descent. It's like you are trying to do gradient descent in a quadratic function whose solution is this, the inverse of A times B. But you are doing gradient-based optimization in a smart way, in the sense that you start at some point and then you follow the gradient and you make like an optimal step in that direction. And then the next gradient that you consider that gradient to be orthogonal to the previous step. So you are making steps that are orthogonal to each other. And this guarantees that if your problem has dimension D, in D steps, you get the solution. And you can show the pseudocode is written here. I won't go into the details, but this means that you would only need D Hessian vector products to solve this system involving the inverse of the Hessian. Obviously, D, the dimension can be still very large, so you will end up truncating this after some time. So you only do a few steps of this conjugate gradient approach. And it's a different approach. Instead of the Neumann series, you could use conjugate gradients. And some people use this method to approximate working with the inverse of the Hessian. This plot here shows a bit how the two methods work. And I wouldn't say that one is better than the other. I think they probably have different trade-offs. Here, you see the cosine similarity between the two hypergradients and the approximation that you obtain using the Neumann series or the conjugate gradient method. And it seems that the Neumann series seems to be a bit better when you do a large number of steps in terms of cosine similarity. This would be like the direction of the gradient, which is what you care about. The magnitude of the gradient is maybe not that important. The magnitude, it seems that conjugate gradient is better. But yeah, I wouldn't be like saying conjugate gradient is better than the Neumann series. The main advantage of the Neumann series, as we're going to see, is that it has some connection with differentiation through the optimization process, as we're going to see later. Good. Any questions on this? No? So just to recap, we want to compute products of the inverse Hessian times some matrix, and that's intractable. We are doing approximations. We are approximating the inverse Hessian times a matrix with a power series or with a conjugate gradient method. And this power series of the conjugate gradients operate using Hessian vector products. Good. That's one approach. There is another one, which is just differentiating through the optimization process. This is called unrolling the optimization, differentiation through optimization, or I don't know, there are different names. And the idea is that you are going to start with some initial value of W, and at the end of your optimization, you will get some W star, okay? And you just apply your optimizer. Maybe if it's gradient descent, you just update several times your weights following the gradient. That's what is shown here. You evaluate the gradient loss, you update your weights, you evaluate the gradient loss, you update the weights, and then you evaluate the validation error. And then you will be differentiating through all this process. That's fine, you could do that, and you avoid having to work with the inverse Hessian. The main limitation with this is memory, because to do this back propagation step, you will need to store all the intermediate weights through your optimization, okay? This means that if you have a huge network like a transformer, massive, and you are doing maybe 100 updates of your weights, you need to store 100 times that network in memory. That's not going to work. So this works only if you do a few steps, okay? And it can be memory intensive. So that's why it's not widely used. You will only maybe do a few steps, maybe 1 or 2 or 3 steps, and that's it. They use something called truncated backpropagation through time, okay? When you just do a few steps of this operation and you calculate the gradients. And as I said, this is memory intensive. There is an amazing paper by David Juveno where he found some smart way to store all these weights, okay? The intermediate weights, he was finding a way to store how the weights were changing, and he was storing them in a compact way, and he was able to differentiate through the whole training process with many, many steps. But in general, for very big networks, that's going to be too expensive, and you won't be able to do it. Good. Any questions on this? No? Good. So that's one approach that we could do. And then the other alternative is something that is going to combine ideas from the first approach using this Neumann series approximation and the second approach that differentiates through the optimization process. Okay? And these things that I am going to describe now, this third approach is based on these papers, this first paper by David Juveno, and then this other paper with some of my students where we extend the previous method by Lorraine, Bicol, and Juveno, so that it handles also optimizer hyperparameters like learning rates and other things. This original work, it didn't allow you to tune like learning rates or momentum or so. It was only able to tune weight decay parameters or other parameters like this pseudo data, for example, that we talked about before. Good. So let's have a look at how this works in practice. We're going to be using updates of the weights to an optimizer. And we're going to have that the next value of the weights, Wi, the weights obtained at the step I, are the weights obtained at the step I minus 1 with some update function. And this update function is going to be given by your optimizer. Okay? If it's Adam, it's going to be the Adam update function. If it's a stochastic gradient descent, it's just the gradient times Adam rate. This update function depends on the previous weights, obviously, and on the hyperparameters, lambda. And the previous weights and the current weights, obviously, they all depend on the hyperparameters, lambda. So we have this weight update function, we call it U, and as I said, in SGD, for example, it would be just the learning rate times the gradient of the training loss. This could be like a mini batch gradient. This could be like the learning rate times the gradient of the mini batch. Good. And now let's see what happens if we differentiate with respect to the hyperparameters. Okay. So we have now, we have the update here for the weights. And now we're going to differentiate with respect to the hyperparameters on the left and on the right. And let's see what happens. It's going to be maybe a bit complicated because there is like a recursion here, because Wi depends on Wi minus 1, and Wi minus 1 was obtained from Wi minus 2. So we're going to be unrolling the optimization process in the same way as this method, differentiation through optimization or unrolling the optimization process. So now the gradient of Wi with respect to lambda is going to be the gradient of Wi minus 1 with respect to lambda. I just differentiate here in this expression. And then I have here the gradient of U with respect to lambda. And the gradient of U with respect to lambda, again, U depends on lambda in different ways. There is going to be a direct dependence on the update function with respect to lambda, but an indirect one through the weights. Okay, this is the same thing that we have been doing before all the time. We can write it like this, and now we can expand things, writing now, replacing Wi minus 1 with its expression, now going into the recursion. Yeah, sorry, first we can group these things here. So we have the gradient of wi minus 1 with respect to lambda, and then the gradient of wi minus 1 with respect to lambda. We just group those, and we have the identity minus the gradient of u with respect to w times this. And then we expand the recursion. So this thing here, it's expanded using this formula. But we just changed the index. Now it's not I, it's going to be I minus 1. And that's what we have here. Okay. And we start now to see some powers there of I minus the partial derivative of u with respect to w. And this starts to look a bit like this power series from the Neumann approximation. Anyway, you can do it. You will get this expression, which looks quite complicated. There is like a sum and powers and all that. But there are now these powers of I minus this derivative. And this looks very much like the Neumann series. There is a difference. These things are evaluated at different W's. We are basically differentiating through the optimization process. And I said that that was memory intensive. It's memory intensive because all these terms depend on the previous value of the weights. And it means that you will have to have the values of the weights through your whole optimization process if you want to calculate these gradients. This is just basically differentiation through optimization. But it's memory intensive, and we cannot work with that. What we can do is an approximation to reduce memory, okay? This is memory intensive. It requires to store all the weights. What we are going to do is say, oh, you are just optimizing the weights, and maybe your weights don't change that much during your optimization. You are going to make small changes following some gradient, and there are not going to be massive differences. So what you can do is assume that these weights that you obtain through your optimization, they are all the same as the last one, okay? Maybe you can approximate all the previous weights with just the weights you have right now, and then you don't have to store any memory. You don't need any memory to store previous weights. And you can just assume that the current weights are optimal. And if you do that, the previous equation, which looks quite complicated, is just now a truncated Neumann series, okay? You have it here, it's just a sum of powers of the identity. And look at the funny thing, before we had the Hessian. Now, what we have is the derivative of the update function with respect to the weights, okay? It's similar to the Hessian, but not exactly the Hessian, okay? Because your update function could be your Adam rule for updating the weights. If it's SGD, this is now the gradient times a scalar. And then this is going to be the Hessian times a scalar in that case. But with other optimizers, like with the Adam or so on, it will be different. And now the super interesting thing, which I think also is very interesting. Now, imagine that you make the number of optimization steps go to infinity, okay? If you make an infinite number of steps, for sure, all these weights at the end of your optimization, they are the same as the last one. Assuming that you reach convergence, they are not going to change that much once you have reached convergence. So if this thing goes to infinity, actually this is a very good approximation. And now the power series converges to the inverse. And now you don't have the inverse Hessian, which is what you had in the implicit function theorem. Now you have the inverse of the derivative of your optimizer update rule with respect to the weights, okay? So you obtain like a similar thing like the implicit function theorem, but you don't use now the inverse Hessian. You use now something that includes this derivative of the update rule. And now you have here the update rule, the partial derivative of the update rule with respect to the hyperparameters. And now this works for learning rates. The gradient is no longer going to be 0. Now the gradient of your update function is going to depend obviously on learning rates. And yeah, I don't know, I find that super interesting, that you just obtain something that is very similar to the implicit function theorem, but now it accounts for learning rates and optimizer hyperparameters. Okay. Good. Any questions on this so far? No? It's all very clear. Or everyone is very confused. Who is very confused? Okay. So just to recap on what we have done. Just a review of the different methods. We have these different methods to calculate the hypergradient. One, working with the inverse Hessian. It doesn't work for learning rates, but let's try it anyway. You need to work with the inverse Hessian. You cannot do it. You need to do Hessian vector products, and you need to approximate the inverse Hessian using Hessian vector products. So option 2, do a few steps of optimization and differentiate. Problem, it's memory intensive. You need to store all the weights. Second, third approach, which is kind of hybrid, is assume that you do a few steps of optimization and calculate, you are going to do I steps of optimization, and you calculate the exact gradient, you get this thing, which is obviously memory intensive. It's the same as differentiation through optimization. But now approximate the formula, assuming that the weights that you get through your optimization process are all the same as the current ones. So you don't need to store memory or anything. And you get now this Newman, truncated Newman series approximation, but it doesn't work with the Hessian. It works with the gradient of your update rule with respect to the weights, okay? And obviously, if you make the number of steps go to infinity, this Neumann series is going to converge to the inverse of a matrix, and it's going to be the inverse of this matrix. Good. Any questions? Yes.
Yes. Can you please go back to the slide where U is defined?
Where you define U, yeah. It's just, I mean, U is a function I use to update your weights.
Okay. So at the end, if I understand correctly, we are we're assuming that the weights of every step are the same as the ones that we want to converge
to calculate the gradients. Yes, that's right.
Yes, to converge the gradients.
Yes.
And at the end, what we get out is actually the updates of those weights.
What you would get out is like a formula for the hypergradient.
Yes, but
So,
it's based on the updates of those weights where we assume.
yeah, but it's always the same. It's always the update for the last weight.
Yeah.
Because it's the WIs would be always the last weight. So what you get here is now you will have these matrices and they're evaluated on the previous weights, but then you just may evaluate them all. They're all evaluated at the current weight value here.
All right, so that means the last update to the current value.
Yes, that's right.
All right. So you're implicitly taking also the last step or the last weight also into account, right?
Yeah, but by last weights, let me see.
Before the update.
We're going to see the pseudocode, and we're going to see exactly the weights. Yeah, I think they are the last weights. It's just the weights that you have right now. Yes.
All right.
What you would be feeding into this formula is the weights that you have right now.
Yes. Okay. Thank you.
Any question? Any other question? No? Okay. Let me check the time. We're fine. Good. So let's have a look at what's going on. Just to clarify, what we are doing is now, instead of working with the gradient of the loss times a learning rate, which is what you would normally do in SGD, you have this update function. And you could imagine that this update function is now kind of like a derivative of a pseudo loss. And when you have learning rates, you will be just scaling the pseudo loss. So here, this would be like an update with a learning rate of size 1, and the learning rate is hidden inside of the update function. So if you don't consider this approach of you have a learning rate that scales the optimizer step. And in our case, you work with a kind of pseudo loss, which is your update function, and the learning rate scales your pseudo loss. Okay, so you're always taking a step of size 1, but you're now scaling your pseudo loss. I don't know, it's just like an intuitive thing of what's going on. The key thing is that you are just making always the same update. It doesn't depend on learning rates or anything, but you work with this update function U that represents the gradient of some pseudo loss that depends on the optimizer hyperparameters. Good. So how do you put all this in practice? Let's have a look at it. Your hypergradient is going to be as follows. This term is 0, you forget about it. This is trivially obtained, the gradient of the validation loss with respect to the weights. And now you have the gradient of the optimal weights with respect to lambda. And you're going to approximate that using your truncated Newman series approximation. But we are using now the gradient of the update function with respect to the weights. And you also the gradient of the update function with respect to lambda. The idea now is to put all this into practice in an optimizer that is running in an online fashion. You are optimizing your weights as normal, tuning the training loss, minimizing the training loss. But every once in a while, for example, every 10 updates, you calculate the hypergradient on the hyperparameters and you update the hyperparameters. Okay? You don't do it all the time because this has an overhead. So you do it only 10 times, and you don't really reset the weights after the hyperparameter updates. You just keep the weights as they are, and you just continue as usual. And in this truncated power series, in this truncated power series, I could be something like 5. We're going to see later some sensitivity of this method to different values of i's. And now these products, you will have to do products with respect to this matrix. This is also like the Hessian. This is a matrix because this is U is a weight update. The output of U is dimensional number of weights. And if you are computing the gradient of this with respect to the weights, you get a matrix that is like the same dimension as the Hessian. You cannot work with this in practice, but you can do efficient matrix vector products as before. You are going to use the same techniques to avoid working with very big matrices. The whole pseudocode is written here. It looks kind of complicated, but it's simple. It calculates this hypergradient, as shown here, as follows. First, you just do gradient-based optimization of your weights using the gradient of the training loss. You just perform maybe T updates. I said this could be 10. They're going to be updating 10 times your weights by looking at the mini-batch gradient on the training loss. Then you're going to start approximating this. You initialize these vectors with the validation loss gradient with this term. This is very easy to obtain. It's just a vector of dimension, the number of weights. And now you're going to multiply this by the powers of the matrices. And you just do multiplying the vector by I minus this matrix, and then you get the result, and you multiply it again by I minus this matrix. And the product with this matrix, with the massive matrix, you do it efficiently. And that's what is done here. V is the validation loss gradient, and that's going to be when you multiply it by I minus the matrix, that's V, and then you multiply U by V, and then you do a backdrop. Okay? And then you do this I times. It will be, for example, 5 times. Here you are doing the kind of Hessian vector products efficiently. And then you just need to multiply by this term, which you do it with another Hessian vector product. I mean, it's not a Hessian vector product, but it's like a similar approach. You multiply whatever you got by this vector U, and then you differentiate with respect to lambda. And that's it. This is the whole thing. It's just update weights for T steps, 10, and then you have this small loop that calculates the hypergradient, and it requires a total of I Hessian vector products. Any questions on this? Yes.
Is it problematic to consider hyperparameters that change the shape of W, that, for example, extend the vector
As soon as you do like a smooth approximation, it should be fine. But the problem might be with the smooth approximation. You could imagine something that in the lines of what you said, that maybe you multiply W by a scaling constant that maybe gets rid of dimensions of W. Maybe it sets them to 0, for example. You could think about doing something like that. It will be like a smooth, you will have to do like a smooth approximation to reducing the dimension. But in principle, it should work. Yeah. One question? Yes.
Maybe just a continuation of that. So if you have a hyperparameter like u/no or not, I mean, you can make a smooth approximation, but how stable would it be with respect to kind of just this 0, 1?
I have no idea. I never tried something like that. I don't know. Try it and see if it works. Yes. More questions?
Like there's some assumptions about the convergence.
About the
convergence of the last function. What about in online settings? Do you think
convergence? Yeah. So that, I mean, the assumptions are there. You assume that the weights in the past, they are the same as the current ones. Obviously, at the beginning of the optimization, that's not going to be true. But you can think that as you are close to convergence, that's going to be more and more accurate. I don't know. It's something that is an approximation, and you will have to see how things work in practice to see how bad that approximation is. I cannot really say more. My assumption is that as you are converging, this approximation becomes more accurate. Good. Yes?
Yes, just very short, continuing on the last question. So if I understand correctly here, it is assuming we're using update functions that don't change over time, right? Like,
yeah.
Okay.
I mean, it's the same. It's like simulating the previous updates using the current one.
Yes.
Yeah.
Thanks.
Good. So how does this work in, yes, one more question.
Sorry.
Yes.
It's a very small question. We are assuming that these hyperparameters are not dependent on each other, right?
Don't depend
on each other, like one or two parameters are completely separated, like continuously.
I mean, they could depend on each other. I think it might be fine. You could say, I define a hyperparameter that is maybe twice another hyperparameter. You could do that, and it should be fine. Your gradients will account for that.
But the update function is like based on if this hyperparameter, like the last step of the hyperparameter.
Can you repeat this last thing?
For the update function?
Yes.
So it depends on the hyperparameters.
Yeah, it will depend on the hyperparameters, but I mean, you could parameterize your hyperparameters in any way you want. So your function u here, this will depend on the hyperparameters, but you could say, I mean, you could have one hyperparameter represented with a scalar, and then you have maybe another scalar for another hyperparameter, but maybe you multiply it by the first hyperparameter. I don't know. Maybe one hyperparameter could be the range of some weight somewhere, and there are some scaling constant somewhere, and then the other hyperparameter could be that scale times another constant. You could have this type of dependencies, and it would be fine. You shouldn't have problems. So let's have a look at how this works on a toy problem. This is a toy problem. It's the UCI energy problem. We use a small network with 50 hidden units. And now we are tuning learning rate and weight decay parameters. And what this shows in this plot, now we have the learning rate on this axis, and then we have the weight decay on this axis. And the colors, they represent how neural networks with different settings of weight decay and learning rates perform on validation data. And you see that there is this region where you obtain better results for settings of the learning rate and the weight decay. This is final test error. We want to go down here. And what is interesting, we show here trajectories that you obtain through training. And what we find is that if you are initialized maybe in a point that has a poor learning rate, the method is making the learning rate smaller, moving it towards better solutions. And the same here, we see that the trajectories, they seem to concentrate to move towards this region of performance. So it's kind of making the right thing. And now we see here how things change as you update the the number of times t at which you optimize your hyperparameters, you can update more frequently or less frequently. And then I, which is the number of elements in your power series, truncated power series. And blue, lower is better. Here, this would be like the test loss. And what we find is that typically values of 5, as I said, for the number of elements in your power series seems to be relatively good. And we just choose also 10 for the update interval. But the differences are not like massive if you update more frequently. So it seems that 5 and 10 works reasonable, and that's what we choose. Maybe it's going to be problem dependent, and some problems maybe you can do better with other settings, but this seems to be okay. What is interesting is that if you use a small value of I, maybe 1 or 2, you get worse results, okay? And this is what you would do normally with differentiation through optimization. You would use just a small number of updates. So you can get a bit better by using larger values of I, which is interesting, at least just to motivate this approach. Let's have a look at some simple baselines that we use to compare. There is this method proposed by Biden and others. It's something relatively similar, but it just optimizes on the mini batches. You just basically update your weights and evaluate the next mini batch, and then you differentiate through that. So you do one step only. So it would be like the same as I. It would be like the same as just the I equal to 1 here. And these authors, they only use it to tune the learning rate. So how does this work in practice? We compare here different methods. These are 3 problems. Okay, these are relatively small problems. We use neural networks with 1 layer and 50 hidden units. We start with different random values for the hyperparameters, and then we do fine-tuning as we train. So we are tuning hyperparameters in an online fashion during training. We start from 200 different initializations, and then we have different methods. Our method that tunes weight decay and learning rates. We tune weight decay, learning rates, and momentum. And then we tune weight decay, learning rates, 1 learning rate per weight. So we have a huge number of learning rates here, and momentum. And then we compare with differentiation through optimization, which would be the same version as this method that tunes weight decay, learning rate, and momentum, but it's not using the approximation that we do. Like it's just storing the weights during the 5. It does like differentiation through 5 update steps. We also compare here with base-off, that is a batch method. It's just training fully, getting some performance, and then trying different parameters, training fully, and getting a different performance. This base-off method runs the method 30 times. Our method just runs the method 1 time, so it's much faster. Obviously, base-off does very well because it's just exhaustive brute force optimization. But we see that here, when we tune all these hyperparameters, we obtain, on average, better results. Yeah, we cannot improve over differentiation through optimization because that method only tunes 1 learning rate. These are only small problems. We tested it on larger ones. Yeah, this shows how the learning rate changes. For one of these runs, you start with some initial hyperparameters, and then it's tuning the learning rate. And we see that it's increasing the learning rate up to some value. At least this is what we see in this method. This would be the best performing method in our case. Yeah. We tried it on bigger networks, LSTMs. This was before transformers were so popular. So we tried this on LSTMs, on some language modeling problem, ConfNets. In this case, tuning 1 learning rate per dimension didn't actually perform better. It seemed to perform worse. our impression is that this was probably overfitting on validation data, because you are tuning so many parameters now that you can do very well on validation data, but maybe in the test performance might not be. And what we find is that tuning weight decay, learning rate, and momentum works better with our method. Interestingly, better than this differentiation through optimization. Why is exactly that? I wouldn't know. Cool. Running times. You say maybe this is very expensive. Actually, it's not that expensive. For example, random. This would be just a standard training with one method, and you do on average like this. On MNIST, for example, it's like, I think this is seconds. I think it's 350. But then I think we train this quite long. You shouldn't have to train this that long, at least on this. Our method, for example, that tunes learning rate, momentum, and weight decay, it's only doing about like twice slower. So just running twice your method, you are tuning these hyperparameters, and you are doing quite well, which is quite interesting. The method that tunes one learning rate per dimension obviously is more expensive here. And the bigger your model, the more expensive it is. And here we see it. I mean, it's still doable, but it's going to be significantly more expensive. And as I mentioned before, we didn't see it performing better on bigger models. So, but yeah, the question is, you can get similar performance as just when you tune these hyperparameters, but the cost of that is that maybe training your model twice. Between 2 and 3 times. We compare with this random method. Is there here? Okay. So there is this random, because it's like 3 times at most, 3 times more expensive. We compare just choosing 3 random hyperparameter values and reporting the best performance of those. And obviously, it's way worse, the random approach. More things. You can combine this with population-based methods for hyperparameter tuning. Like we have mentioned this in the introduction. You have this successive halving algorithm or asynchronous successive halving algorithm. Actually, they are very successful. You just train many models for a while. You pick the best ones and then get rid of the worst ones and then continue training. And this is a very effective method to tune hyperparameters. You can still do it with hypergradient-based methods. You just optimize everything jointly, and you start with different random initializations. Some of your random initializations may be better, and others worse. But you can combine this approach with this ASHA technique, which is a state-of-the-art method for hyperparameter tuning in neural networks. Actually, you get gains there. For example, I think with PPT, we didn't get that many significant gains, but ASHA is better. And what we see is that ASHA, for example, we get results here and here that are much better than what you would obtain with ASHA running for very long. Okay, it's like this is like more than 10 times faster. So you can still combine this approach with ASHA, which is quite interesting. This is like not like a very exhaustive evaluation. So this was something like an extra thing that we did, but it would be interesting to see very exhaustively what are the potential gains. Maybe some point to conclude, could you maybe scale this up? These are maybe some random thoughts that I had on maybe potential future work in these directions. We have this Neumann series approximation, the truncated Neumann series approximation to the Hessian. It would be this thing here. And this can still be expensive if you have especially maybe very big models. And maybe you want to do something faster. So if this looks like a bit like a Hessian, maybe you can approximate it with something, I don't know, you have methods like Adam that scales the gradients. Maybe there could be opportunities to replace this with something similar to what Adam would get, but maybe operating on maybe this thing instead of the normal gradients. I don't know. This is something that I didn't try, and I think it would be interesting maybe for someone to explore more these directions. Yeah, so just to conclude, I have mentioned here this approach for hyperparameter tuning using gradients. It can handle any gradients of optimizer hyperparameters and of other hyperparameters like weight decay and so on. It's scalable to a very large number of hyperparameters. It only requires one training episode, so it's like an online method. You just train your method and jointly tune learning rates, hyperparameters, and weights. We have seen that it has outperformed other baselines, and you can also combine it with Asha, for example, and then get even better results. So yeah, that's all. Thanks everyone, and yeah, if you have more questions, I'm happy to.